So, quadratic optimization. Now that word optimization, that just means like finding the most efficient, the most economic, the best outcome. So that's what we're doing. We're finding the optimal solution. In terms of a quadratic, what it means is the maximum point, okay, if it's opening downwards, or the minimum point if it's opening upwards. Okay, so sometimes we want to find the minimum, sometimes we want to find the maximum. Now we know this formula here, minus b divided by 2a, that is the x coordinate of the turning point, the maximum or the minimum. Okay, that will always be the x coordinate, the maximum or minimum. Remember, if a is positive, it will open upwards, which means we would have a minimum. And if a is negative, it's going to open downwards, which means we would have a maximum. So we'll just go through an example here together that's not listed in your book, just to point out what we would look like with a normal quadratic. We have x squared take 5, 4x take 5. We're going to find the coordinates of the turning point, okay? So firstly, we can see that the a value is positive, all right? So a is positive, which means it's going to open upwards, which means we're finding a minimum. We have a minimum coordinate. Okay, so this will be a minimum. Now, the way we find the x coordinate is that it's minus b divided by 2a. So in this circumstance, what we have is we would have minus, and the value of b is minus 4. And we're doing that divided by 2 times the a value, which is 2 times 1. So here we have two negatives will become positive. 4 divided by 2. This gives us the x value is 2. All right, so all we're doing is putting a and b into this formula and processing to determine the x value of the minimum. So if we think about the minimum, it has an x value of 2, and then we're asked to find the corresponding y value. Well, look at this. Y equals x squared take 4x take 5. So all we have to do then is put the number 2 into this function. We can say when x equals 2, y is equal to, and then I'm just going to substitute the number 2 into this equation. 2 squared take 4 times 2 take 5. Okay, so it's going to be 4, take 8, take 5. So minus 4 take 5 minus 9. So the coordinates then of the minimum, x is 2 and the y value is minus 9. Now that's how the exercise will start. And we can check our working by graphing it and then pressing G-solve. We can G-solve the maximum point or the minimum point depending on the situation. Now let's look at a context. Okay, so in our first example, we have the profit in manufacturing X kettles per day is given by this quadratic equation. Find the number of kettles to maximize profit and the profit in this circumstance. So I've gone ahead and sketched this curve. All right, if you graph this, this is what the quadratic looks like. We know it's going to have a maximum point because the a value is negative. If the a value is negative, if it's less than 0, it's going to open downwards, so it will have a maximum point. So we want to know what's the coordinates of that point, right? Now, we could solve this just by graphing it and G-solving it. Okay, that's a way we can check our answer, but we're going to use these quadratic techniques. What we have along here is the number of kettles, and what we have along the y-axis is the profit. All right. Now you might think, oh, just make more kettles, you'll get more profit. However, if you're running a factory for a really long time, you're going to need to pay people overtime. You need to maintain the machinery and so forth. So it's not always efficient to make as much as you can. There is some optimal amount, some amount that generates the maximum profit. Okay. So we want the number of kettles on the x-axis and the profit on the y-axis. So what we'll do is we just go, well, x is minus b divided by 2a. That's the formula we're going to use. In this circumstance, it's minus 564 divided by 2 times minus 3. And you can type it into your calculator like that, or you could simplify it to go like this. It doesn't matter. Minus 564 on top of minus 6. Both of them are negative, which means our solution will be positive. And so when we evaluate this, we get positive 94. So x is 94. X is the number of kettles. So 94 kettles produces the maximum profit. Alright, so we can type all of that into our calculator. Next, we want to know what is that profit. Alright, so now all we're going to do is we're going to put the number 94 into our profit function. So we're going to do P of 94. When X is 94, what's the corresponding Y value? So we have minus 3 times 94 squared plus 564 times 94, take 1200. Alright, so we're definitely relying on our calculator for that one. 25,308. And a unit, it's in dollars. Okay, so we have an example with the algebra. We have an example with a profit equation, so it's given a context. But now we're going to move into a little bit more problem solving and show you the kind of thing we can start to anticipate in a test. We have a chicken cage is erected against a wall. Given there is 30 metres of fencing available, what is the optimal shape? So here's a wall, might be an existing shed, might be a fence or something like that, and we're going to build a chicken cage against the wall. We have 30 metres of fencing. So that means we're going to stick with these dimensions, x, 30 take 2x, and x. Now the reason that's the case is because if we add up the perimeter of this shape, x plus x, that would be 2x, plus 30, and then take away 2x, well the x's will cancel and I'm left with 30. That's how much we have. And we want to know, well, what are the dimensions? How big should this be? Because as you change the dimensions of that rectangle, the area will change. The area of this rectangle will change as we change the value of x. So the area of this shape, right, the area of this rectangle is equal to the length times the width. X times 30 take 2x. Now, if we expand this, this is 30x, take away 2x squared. This is a quadratic equation. All right? And so we could put different values of x in there to determine the area, but we want to know the optimal solution. Firstly, we have the a value. The a value is negative. In this circumstance, right, a is minus 2 and b is positive 30. That's because a is always the coefficient of x squared. It's always the number in front of the x squared term. So we have a is minus 2 and b is 30. Because a is less than 0, it's negative, it's opening downwards. We're going to have a local maximum. All right. And so we're going to say, well, the x coordinate of the maximum is minus b divided by 2a. In this circumstance, minus 30 divided by 2 times minus 2. We have 30 on top of 4. 30 on top of 4 will be 7.5. So the x value is 7.5. That gives us the optimal area. So if we have x is 7.5, all right, it means this length here is 7.5, this length here is 7.5, and this length here is 30, take away 2 lots of 7.5, that's going to be 30, take 15. This length here will be 15, okay? Now, it says, what is the optimal shape that generates the most area? So in order to answer the question right, all we have to say is the shape, it's a rectangle, and it has dimensions 7.5 by 15 meters. And right there, we've successfully answered the question, but I just want to draw something out for you guys. So that's an area of 112. If you evaluate this right, the area you get is 112 12.5 meters squared. That's the area the chickens play in. But let me show you, if we had different numbers, this is the maximum solution. If we had different numbers, all of them are going to be less than it. This gives us the most area for the chickens. So let's just do a different value of x. Let's suppose x was 6, okay? So in the circumstance where x is 6, this length here is 6, and this length here is 30, take away 2 times 6, it's going to be 18. And 6 times 18, 108. Okay, so I said this is the optimal solution. All other dimensions of this shape will have a smaller area. This gives us 108 meters squared, whereas this gave us the 112.5 meters squared. All right, so we can use quadratics to find the optimal solution. Now we won't go through question 3 just yet. Let's get you guys to crack into question 1, 2, and we should be able to access 3 and 4 of the textbook for now. And a bit later, we'll check in and we'll... Okay, so we have here 6 pens. All right, 6 identical pens to put your pigs or chickens or whatever in. And we have 1,200 meters of fencing available. So part A says explain why 12x plus 7y equals 1,200. Well, all we have to do here is observe from the shape we're required to have. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 lots of x. Okay, so there are 12 lengths of x. 12, sorry. There are 12 lengths of x. And 1, 2, 3, 4, 5, 6, 7 lengths of y. That add to 1,200 meters fencing. Okay, so that's a pretty good explanation. We're just saying, comparing the shape with this statement here. Okay, show that the area of each pen is given by this equation. Here it is here. Show that the area is this. Well, the area of a pen, right? The area of a pen, each pen is going to be x times by y. That's going to be the area of a pen. However, the problem with this is that we have 2 variables. We want just one variable. And so what we're going to do is we're going to manipulate this equation here to get x by itself, or to get y by itself. So I'm going to come up here, we've got 12x plus 7y equals 1,200. We're going to get y by itself so that we can substitute it into this equation. So the first thing we'll do is we'll take 12x from both sides. And then we're going to divide both sides by 7. Okay, so now the area of each pen, we know the area of each individual pen is x times y. So we have a substitution we can perform for y. We can substitute y in here and it gets rid of the variable y. It's just in terms of x. The area becomes x times 1,200, take 12x on top of 7. Okay. Now, this formula here, this is actually for all of the pens combined. So we are going to leave that one. We won't deal with that formula. rather than just stick to this formula that we've got here. So we have, that's the formula for the pens. Now, we're going to process it a little bit so that it looks more like a quadratic for us. And the way I'm going to do that is distribute the x. Now, whenever we have a number times a fraction, it always goes to the top. The denominator stays the same. What's technically going on is we have x on top of 1. Whenever we're multiplying fractions, it's the top times the top and the bottom times the bottom. So this means at the bottom we're going to have 7, and at the top we're going to have 1200x and take away 12x squared. Alright, so that x has distributed to both of those. And then what we'll do is split this denominator. So it becomes 1200 on 7, lots of x. Take 12 on 7, lots of x squared. Alright, so that is the quadratic that gives you the area for each individual pen. Alright. So we're going to I need to fix the notebook there. There's a little error there. That's for all of them combined. Okay, find the optimal solution. So now that we have the equation for the area, all we're going to do is x equals minus b on 2a. In this circumstance, we have minus 1200 on 7 divided by 2 times the value of a. Okay, so that looks pretty confusing like that. All right, you can type it into your calculator, and as long as you type it in right, you'll generate the right solution. But I might just do this a little bit manually to reveal to you a few operations that are going on. Firstly, we'll multiply by the 2. So 2 times minus 12 is minus 24. And we have one fraction divided by another. Now, whenever we have one fraction divided by another fraction, it's equal to the top and the bottom multiplied together, divided by the 2 middle ones multiplied together. So in this circumstance, the top times the bottom, so minus 1200 times 7, and 24 times 7. Okay, the 2 middle ones multiplied together. Alright, so then we got 7 at the top, 7 at the bottom. We've got 1200 on 24, which will be 50. Okay, so the value of x is 50. Alright, we've found the value of x. That gives us the optimal solution. However, we need the value of y. What's the corresponding value of y? Y is 1200, take 12x on 7. So we can say when x is 50, y equals 1200. Take 12 times 50, divided by 7. And that we'll just have to evaluate. 12 times 50 is 600. So we have 600 on 7, which will be 85.7. Okay, so to answer the question, all right, with 1200 meters of fencing, the dimension that we have is 50 by 85.7. Okay, that's our optimal solution. Other shapes or other dimensions will give you a smaller area. This is the maximum area. Now I'm just going to take you through that one again, not to do it all, just to point out what's the strategy we follow. You will see these pop up in the practice tests. Okay? What we've done is we've started with this shape and we're given this equation. You're given this and you're told, explain why this is true. Well, we can see from the shape there are 12 lengths of x and 7 lengths of y and 1200 meters of fencing. Okay, so we have that equation. Then it says, hence show that the area is this. Well, the area of each individual pen is just the length times the width, right? X times y. Okay, so we've done x times y. But the problem with that is it's one variable. Now, there's two variables, sorry. We need one variable. And so we take this equation. You're not given it for no reason. We're given it for a reason. We rearrange it to get y by itself. We've got y by itself and we substitute it right there where the y is. Then we evaluate that and we generate our quadratic. Once we have our quadratic, minus b on 2a, we get our optimal solution, x is 50, and then we say, well, what's the value of y that supports it? We find the value of y. There's our answer. Okay, so everyone, we've got time. Let's have a go at question 5 and question 6. Both of those follow a pretty similar sort of pattern. Let's give it a crack.